Signal flow graphs. Okay, signal flow graphs may be regarded as an alternative representation of a block diagram. Let's see here. For example, if you have this kind of block diagram, we can represent it in the signal flow diagram as like that. We have an arrow here, input, output, and above the path we have gain. For this path we have GS, as you see. What about the other one? In here we have a cascade system. So RS, from RS to AS we have G1S as gain, and from AS to YS we have G2S gain. What about the parallel system? As you see here, we have two paths in parallel connected to each other. RS G1S, this path, and RS G2S, this path. And we can get YS as like that. What about the feedback system? We have RS, after the comparator we have ES. In here we have 1 as gain, because as you see here we don't have any gain between the RS and ES, so it will be 1. After the ES until YS we have GS gain in this path, and from YS to ES we have also negative feedback which gains HS, but minus because of the negative feedback, and then YS which is explained after. Okay, this is the forward gain again. Input-output representation in block diagram can be given as like that. When constructing an SFG signal flow graph, junction point or nodes are used to represent variables. Okay, nodes are used to represent variables. In this case, US is the input variable here. In here, RS, we can say. YS is output. As you see here, YS is output. The nodes are connected by line segments called branches. This path called as branch. According to cause and effect equations, the branches have associated branch gain and direction. It's so important to write direction in the signal flow graph. In an SFG, signals can transmit through a branch only in the direction of the arrow. Okay, it's so important. Signals can transmit through a branch only in the direction of the arrow. So, if you have this kind of signal flow diagram, you can directly write YS and RS relation as GS. It is the same with the block diagram. It is an alternative way to get a transfer function or gain of the function. In here, for example, YS over RS can be obtained as G1S times G2S. For this system, A2S plus A3S, which means RS times G1S plus G2S. For this notation we have some rules which called as SFG algebra. The value of the variable represented by a node is equal to the sum of all signals entering the node. Okay. For example, if you have this kind of signal flow diagram, what can we have for the Y1 point, Y1 node? Y1 will be sum of the input to the inside. As you see here, we have one, the other one, the other one, and the other one. All four terms will goes to the y1. So we can represent the y1 as a21 times y2 plus a5y1 times y5 plus a31 times y3 plus a41 times y4. Okay, we can write as y1 as like that. What about the others? As you see here, we have another terms here. For example, y6 will be y1 times a16. What about y7? y7 will be y1 times a17, and finally y8 will be y1 times a18, as you see here. What about the parallel branch? If you have parallel branch as like that, we can directly write it the sum of this. If you want to get y2, don't consider this branch. What we have, y2 will be a times y1, b times y1, and c times y1. So parenthesis by y1, we will get a plus b plus c. So we can represent with a one branch as like that. What about the series or cascade connection? What we have, for example, for this kind of system, for y1 and y4 relation, we can directly multiply these gains between them. Okay, y1 a1 to a2 3 and a3 4. What about the feedback system? In here we have feedback. For the ys we can write es times gs, as you see. What about es? Es is equal to, we have one rs and minus ys times hs. So if you write into the first equation, you can get the ys as rs blah blah blah. Ys will be rs minus ys hs times with the gs. So it will be rsgs minus gs hs ys. Ys will be gs 1 plus gs hs times rs. We can directly get it as like that. Yes, if we have this kind of system, what will we do now? Okay, as you see here, we have some kind of variables such as r, e, y3, y2, y1, and y. And we have some gains such as g1, g2, g3, g4, and we have feedback gain such as h1 and h2. How can we get now? We will use not for all variables, okay? For example, it is r. And then we will get e, and then we will get y3, E, Y3, Y2, Y1, and Y. Between the R and E, we don't have any gain, so we can say it will be 1. And E and Y3, we don't have again any gain, so we can say it will be 1. Between the Y3 and Y2, we have G1. Y2 and Y1, we have G2. Y1 and Y, we have G3. What about the others? For example, where is the G4? Between the Y2 and Y. Y2 and Y. We have another forward path. It will be G4. We don't have any other forward branch, but we have 3 feedback, as you see. Where is it? From Y to Y to R, Y to E, sorry. Y to E is one of them. It will be H1 or minus H1. It will be minus H1 because of the negative feedback. And also we have another feedback from Y to Y2, as you see here. Again, it is negative feedback. It will be minus H2. And the last one from Y1 to Y3, Y1 to Y3. It will be, sorry about that, from Y to E, we have minus 1 only. This is negative unity feedback. From Y1 to Y3, we have minus H1. Okay, we can directly draw the signal flow diagram by using the control block diagram as like that. Yes, as an example on the construction of SFG, consider the following set of algebraic equations. Y2 is as like that, Y3, Y4, and Y5. So we can say we have 5 nodes which are Y1, Y2, Y3, Y4, and Y5. As you see from the algebraic equations, we don't have Y1 equation. So maybe we can evaluate this condition. Y1 may be input for this system. Okay, so we can start from the Y1. Assume that it will be Y1. Then Y2, Y3, Y4, and Y5. What is the Y2? Y2 is A12 times Y1. So we have a branch here and the gain will be A12. And the other term is comes from the Y3. So we have a branch here and the gain will be A3 and 2. So the Y2 is finished now. What about the Y3? Y3 has a branch from the Y2 which the gains A2, 3. And the other term comes from the Y4 and the gain will be Y4, 3. So Y3 is finished now. What about the Y4? Y4 has Y2 term, so we should get a branch from the Y2 and the gain will be A2, 4. and comes from the other term from the y3, and the gain a3 and 4, and the last one a4 4 y4. It means we have another branch from the itself, and gain will be a4 4. What about the y5? We have a branch from y2. The gain will be a2 5, and the other term will be comes from the y4. The gain will be a4 5. Okay. By using the algebraic equation, we can directly get the signal flow diagram as like that. Okay, let's continue definition of SFG terms. Input node. Input node is a node that has only outgoing branch. I can say this: input node has no input from anywhere. Okay. For example, let's evaluate this diagram. What can we say about the input? Let's examine now again. Input node has only outgoing branch. Okay, we don't have any incoming branch. So if you talk about this diagram, y1 has no incoming branch, as you see. For the y1, we have only outgoing, sorry. What about the output node? Output node is a node that has only incoming branch. Let's evaluate it in this diagram, for example. What can you say about this diagram? Which node can be the output for this system? If I do a modification on this diagram, for example, if I add another node to here with the same label y2, and if I send with one gain as like that, what do you think about this? Now, output node has only incoming branch. Okay, has only incoming branch. We have only one output because of the incoming branch. As you see here, y5 only incoming branch, such as y4 a4 5 and y2 a2 5. But we don't have for the y5 any going branch to somewhere. But if you modify this signal flow diagram as like that, I add a node here, which is y2, and gain will be 1. First of all, think about this. It can be done or not. It affect to the system or not. We can do this operation, this modification, because it is not affect to the system. If you do this kind of additional node, it means y2 as evaluated now as output. If we summarize this, an input node has only outgoing branch, and output node has only incoming branch.